This video is the second part of topic 5 on transition metals. We're going to look at the strength of different ligands and ligand replacement reactions and then some vanadium chemistry. Let's look at how we write a ligand replacement equation. This equation we're going to look at is the addition of ammonia to copper ions in solution. Copper ions in solution are hexa aqua copper ions, and we've met those previously. And we're going to substitute 4 of the water ligands with ammonia ligands. And we form an ammonia and water complex, and we've displaced 4 water molecules. In ligand replacement, 2 factors are considered: the relative strength of the ligands and changes in entropy. The definition for ligand strength is that it depends on the availability of lone pairs of electrons to be donated to the metal atom or ion. The relative strength of a ligand is shown in the diagram. If we look first of all at the halides, we can see that as we go down the group from the chloride to the iodide, the ligand strength decreases. And this is because the ion size has increased, so the strength of the coordinate bond decreases. If we look at ligands with oxygen and nitrogen, we can see that lone pairs are more easily donated from less electronegative atoms such as the nitrogen compared to the oxygen. And finally, if we look at amines, alkyl groups push electrons toward the nitrogen atom, so lone pairs are more likely to be donated. Ligands higher in the list will displace those lower in the list, but there is also a concentration effect, as a large concentration of a weaker ligand will still displace a stronger one. Let's look at entropy changes. We met entropy in A2 Unit 1, and it's a measure of disorder. In the example shown, there are 4 species on the right-hand side, but there are 7 species on the left-hand side. This would cause an increase in disorder, which is an increase in entropy. If we look at the example below, we can see that in this case, there is no change in the total number of species before and after the reaction, so there is no increase in entropy. In the case of the complex with EDTA, the increase in entropy is very pronounced. If we look at this equation, we can see that we are changing from 2 species on the left-hand side to 7 species on the right-hand side, and this leads to an increase in entropy. Reversing this change would be very difficult in terms of entropy, as you would have to move from a disordered state to a much more ordered one. Complexes involving multidentate ligands are more stable than those with only monodentate ligands in them. The formation of the chelated complex is favoured because of the increase in entropy. We're going to look at some ligand replacement reactions of hexa aqua copper ions, and we're going to start with ammonia ligands. Our hexa aqua copper ions form a blue solution. When we add sodium hydroxide solution, 2 of the water ligands are displaced and a pale blue precipitate of copper hydroxide is formed. Ammonia solution will also form the same precipitate because ammonia solution also contains hydroxide ions. However, excess ammonia solution added will form a new precipitate because the ammonia ligand is a stronger ligand than the hydroxide ligand. We have now formed tetraamino diaqua copper complex, which is a deep blue solution. Here is an equation for the overall reaction, and this is how our tetraamino diaqua copper complex looks. The second ligand replacement reaction we're going to look at is using our hexa aqua copper ion solution, and we're going to add concentrated hydrochloric acid. When concentrated hydrochloric acid is added, the pale blue solution turns green and finally turns yellow. And it has turned yellow because it now contains the tetrachlorocuprate ions, which are yellow. Here is the equation for the overall ligand replacement reaction, And this is what our tetrachlorocuprate ion looks like. This diagram shows us different ligand replacement reactions and the complexes that are formed. You'll notice that there is increasing stability as we go from the hexa-aqua-copper complex to the tetroamino diaqua-copper complex. We're now going to look at the colours of complexes. The following colours should be known for the transition metal ions given. So the first table shows the colours of solid transition metal compounds, and the second table gives the colours of the aqueous solutions. As transition metal ions can show a huge variety of colours, it is often possible to identify a complex ion simply by its colour. In Unit 3, you will complete a practical exam, and one of the sections is usually where you have to do qualitative tests on an unknown solid. So it's important that you can recognise common transition metal compounds in their solid state and in solution. For example, here is a green crystalline solid, which is iron in the +2 oxidation state and the associated green solution. Here is the cobalt 2+ ion. The salt is pink and it dissolves to give you a pink solution. Here's iron 3, again getting an orange solution. And finally, copper sulfate, which is a blue crystalline solid, giving the blue solution of the hexa-aqua-copper ion. The colour of a complex ion depends on the ligand. In this case, you can see that the hexa-aqua nickel complex is green, but if the water ligands are substituted with ammonia ligands, the complex turns blue. The coordination number, and of course we have seen this by changing the ligand from water to chloride, where we go from a blue solution to a yellow solution. And then finally, the oxidation state of the metal. The precipitation of transition metal hydroxides is a useful means of identifying transition metal ions, and you met this at GCSE level in the Unit 1 topic on testing for ions. All of the following metal ions form insoluble hydroxides with distinct colours. So if you have a look at the first column, you can see the colour of the precipitate when you add sodium hydroxide, and the third column explains what happens if you add excess sodium hydroxide. Here are some pictures of the practicals being carried out. So this was for the iron 3+ ion and sodium hydroxide, the iron 2+ ion and sodium hydroxide, and the copper 2+ ion and sodium hydroxide. We can replace sodium hydroxide with ammonia, and we will see similar observations. However, they are all not the same. So if you have a look at the table, you can see here that with the adding ammonia to cobalt, nickel and copper, you get slightly different observations than when you add sodium hydroxide. That would also be the same for chromium ions with sodium hydroxide and ammonia. Don't forget that SIA provides the acceptable colour changes and observations document in the support section in the website. So if you have a look here, you can see the table for transition metals and the qualitative detection tests with colours and observations that you would be expected to give in an exam. We're now going to move on to the last part of this topic, which is where we're going to look at vanadium chemistry. Vanadium exists in the +2, +3, +4 and +5 oxidation states, and these ions have distinct colours. Vanadium can be reduced from the +5 oxidation state to the +2 oxidation state using zinc in the presence of hydrochloric acid. Here are the names of the different ions that are present during this reduction with their associated colours. When we practically carry out the reduction from +5 to +2 oxidation states with vanadium, we start by using ammonium metavanadiate. If you have a look at the formula, you can see that the vanadiate ion is VO3+. Previously, when we talked about vanadium in the +5 oxidation state, we talked about dioxovanadium. If we look at both of these ions, you can see that they are both in the +5 oxidation state. On the slide, you're given the practical details for how you would carry out this reaction. We're going to explain our observations for that reaction in terms of standard reduction potentials. This will be covered in more detail in the next topic. If we look at the equations given to us, you can see that in each one, they're half equations because we have electrons, and in each case, the electrons are on the left-hand side. So these are what we call reduction equations. If we have a look, we can see we are given values for each of these equations, and these are called the standard reduction potentials. If you have a look, you can see at the top, you have a positive electrode potential, and that means that that equation will occur and that species will be reduced. If we have a look at zinc, we can see that zinc ions do not want to gain electrons because they have a negative standard reduction potential. So that means that zinc ions don't want to gain electrons, but zinc wants to lose electrons. To work out if the reaction is going to occur, we can see that the standard electrode potentials of all the vanadium reductions are greater than that of zinc. So that means that zinc can reduce the vanadium from +5 to +2. If we look instead of using zinc and we use iodide ions, iodine has a standard reduction potential of 0.54 volts. Now if we look at our values given for going from +5 to +4, which has a standard reduction potential of +1 volt, and then if we look at going from +4 to +3, which has a standard reduction potential of 0.34 volts, we can say that the standard reduction potential for the first reaction is the only vanadium reduction which is greater than the reduction potential of the iodine. So that means that iodide ions will only reduce vanadium from +5 to +4, but no further. Moving on, if we go in the opposite direction and instead of reducing vanadium from +5 to +2, oxidize vanadium from +2 to +5, we can see that if we use the oxidizing agent acidified permanganate, we can oxidize our vanadium 2+ all the way back up to vanadium +5.